Today, okay, yeah, I'm going to have two topics, and one topic is continuous from uh, my first talk in this seminar. So anyway, so today, okay, I will introduce some problem related to network system, and the first part is okay. Uh, Jointly worked with Shimatani and Mitsuno. So they are all my students, Dr. Ko student. And the second topic is joint work with, okay, Ishii, Kondo in Osaka University and Miura and Tanaka. Okay, now, okay, today, okay, I'm going to talk about the two topics, and one topic is some, okay, reaction diffusion systems on metric graph. So this topic is some continuous topic uh, from my first talk in this seminar. And this first topic is just a problem on some network systems like this, okay, such as electric currency or neural actions and like this. And second topic is related to okay, some microscopic network such as signal network and metabolic network. And actually, the some coating patterns on the surface of the skin of the animals like this is determined by the microstructures related to the yeah, skin cells like this. Actually, okay, in skin cells, there are several microscopic structures like this, and as a result, we can observe this kind of macro patterns. Okay, yeah. Then, okay, the problem is, okay, how to connect this microstructure and macro structure theoretically. It's a problem. So anyway, so this topic will be mentioned in the second part of this talk. Okay, let's start, okay, the first topic about the reaction diffusion system on the metric graph. Okay, the metric graph is the graph like this, and we together with some junction point like this, and usually we import the boundary condition. Yeah, usually we import the Kirchhoff boundary condition at this junction point. Okay. Anyway, okay, these problems are related to several phenomena such as liver branch or nerve axons. And for simplicity, we consider this graph as an electric currency. Then the Kirchhoff boundary condition is very natural as the condition at this junction point. And we consider the movement of pulse-like localized patterns along this metric graph. Okay, anyway, okay. This is a problem. Okay, it's a reaction diffusion system on metric graph. Okay, in this talk, okay, we mainly consider the star-shaped graph like this. Star-shaped means, okay, only one junction point like this, and several, okay, half lines construct, and it at some common point as a junction point like this. Okay, anyway, so EJ is a unit vector corresponding to the directions of each half lines like this. And omega j is each half lines. And we consider the reaction diffusion systems on this metric graph. and okay, so suppose okay, U is the some function defined on this metric graph. And then, okay, we denote uj by this definition. That is, the function uj denotes the functions restricted on each half lines omega j. And this is a Kirchhoff. Okay, this is a so-called Kirchhoff boundary conditions. So this condition is imposed at this point O. So actually, this condition consists of two conditions. One is this, and one is this. Okay, and this is okay. Every value equal each other at this point. That is, the function defined on this metric graph is continuous in some sense at this junction point O. That is, okay, all the values are same. And this is okay. Total currency is preserved. This condition is correspond to the means total currency is preserved. Okay, so the sum of all derivatives at this point is equal to 0. So this condition at the junction point is called Kirchhoff boundary condition. So in this case, okay, each paths are quite same each other. So the coefficients are all same. So, but if, for example, okay, the diffusion coefficient is different on each half lines, then this boundary condition is extended like this. That is, some diffusion constant appears in this part like this. That is, the sum is some weighted sum, okay, by diffusion constant like this. So value is same. So this condition is same. So anyway, so we consider this kind of problem for general reaction diffusion system. Okay, so okay, I already mentioned about several results about this problem. So I skip all the things corresponding to the my previous talk, and but very roughly explain as the review. Okay. Yeah, okay. This is a setting I already mentioned. Okay, first we consider the reaction diffusion system. Okay, on the metric graph like this, and with this boundary condition. Okay, then this is some conditions for the stability of pulse solutions. So, but I will skip this kind of detailed condition here. I just mentioned about the result only. So, okay, then, we have this kind of result, which was mentioned in my previous talk. Okay, so this theorem emphasizes that if we put one pulse on each half lines like this, okay, and located, and each pulse is located, okay, L1, L2, and LR like this, and okay, small LR, okay, and total total number of half line is capital R, okay. So then, okay, if we put an initial data like this, then the solution on this metric star graph is keeping close to this function. And this function is defined like this. That is, okay, on, okay, okay, on half lines from 1 to small r, okay, the profile is very close to one pulse solution, like this. And on other half lines, okay, it's close to 0. That is, okay, no pulse solution on other half lines. And only, okay, from only half line from 1 to small r, okay, there is, okay, one pulse localized solutions like this. Then, okay, solutions okay, keeps close to the to this function for any time. And this location is essentially determined by this ordinary differential equation. So this ordinary differential equation, okay, the right-hand side of this ordinary differential equation is given by this function. So a little bit complicated. So, but the some difference of the some quantity and some sum, okay, from 1 to small r, like this. Anyway, so the movement of each pulse solution is governed by this ordinary differential equation, and together with several corollaries. So, okay, so this is main result in my previous talk. So, anyway, so I review this result. And okay, what kind of movement can we know from this ordinary differential equation? So I show several examples. Okay, first, okay, we consider the movement of okay, one pulse solution. So one pulse solution means, okay, we just one pulse on one half lines, and other and on the other half lines, okay, we do not put any pulses. Only one pulse, only on one half line only, like this. Okay, in that case, okay, if the pulse solution itself stable, then the pulse, okay, moves toward the junction point like this. So it is easily known from this ordinary differential equation. So actually, if okay, if there exists only one pulse like this on matrix diagram, then the movement of L1 is governed by this ordinary differential equation from the cell. So, but this right-hand side of ordinary differential equation becomes like this. And we already know this constant M0 is positive if single pulse solution is stable in some sense. So anyway, so this constant is positive. And now this capital R is the number of half lines. So usually this number is bigger than 3. So in that sense, okay, this part is become positive. So R minus 2 is positive, R positive, and M0 positive. And with some minus signs. So then totally this right-hand side is negative in this case. So it means, okay, L1, okay, dL1 dt is negative in this case. So it means this single pulse solution moves toward the junction point. So you can understand theoretically this movement. And actually, okay, this is a very general result. So, but we can apply this result to the several explicit examples of reaction diffusion system. For example, okay, Biedermeier or Gray Scott models. So, yeah, now I just show. So this is the, one example of the Biedermeier model. So this is a model equation of Biedermeier. So in this case, this system has this kind of spike solutions as the pulse solution. So if we put this kind of pulse solution on this metric graph like this, then the pulse moves to the origin. And also, this is the example of Gray-Scott model. In the Gray-Scott model case, this model equation possesses this kind of pulse solution. So, and also for this pulse solutions, if we put such pulse solutions of Gray-Scott model equation on metric star graph like this, then the pulse moves to the toward origins like this. Like this, at least for Biedermeier model and Gray-Scott model, we can prove this kind of move by this theorem. This is a case for the movement of single pulse solutions. So quite similarly, we can consider the movement to single pulse solutions like this. In this case, we put two single pulses on each half lines like this, and on other half lines, we don't put any pulse. Yeah, we just put two pulses, like this. In this case, this location L1 and L2 are determined by this ordinary differentiation. So this is a system. So the movement becomes a little bit complicated. So, but the movement becomes like this. So if R is bigger than 5, so capital R is the number of the half lines constructing of the metric graph. So anyway, so if the number of total half lines is bigger than or equal to 5, then this kind of movement appears. This means if we put initial data like this, then it first goes toward origins. Both pulses first go towards origins like this. So, but after several times, one pulse, so more apart from the, this pulse is more apart from the origin. So this pulse is turns to this, turned opposite like this, and eventually the movement becomes like this. That is closer pulse are still going toward origin. So, but more far pulse eventually go to this direction. So this kind of dynamics is observed from this ordinary differential equation. So similarly, if the total number of half line is 4, in this case, there is some stable stationary state like this. And if the total number of lines is 3, so in that case, just 3 half lines. So in that case, the opposite movement from this is observed like this. That is first two pulse goes apart from junction point, but closer pulse turns opposite like this, and eventually this pulse toward the origin, and another pulse toward far from origin like this. So this is the case article 3. So like this, we can analyze some precise movement of pulses on metric star graph like this. So this is some application for this theorem. Okay, anyway, so this is a very, very okay, rough review of my past talks. So, okay, yeah, this is okay, proof, okay. So I skipped this part. And okay, in today's talk, I would like to a little bit extend of the previous result like this. So that is okay. Okay, one okay extension is this. Okay, so the diffusion constant is different depending on its half lines. In that case, okay, Kirchhoff boundary condition at the junction point becomes like this. So some okay weight correspond to diffusion constant appears like this. Okay, and another application is okay a very thin domain limit problem. So this problem originally okay proposed by Yanagida-san. Okay, so yeah, actually in 2001 first, Yanagida-san just considered this kind of problem or some scalar equation. So this is some scalar equations. Okay, the typical example is an Arenkan equation with this non-linearity, and this equation is considered on this thin domains with width epsilon dx. So and here okay epsilon is sufficiently small. So this width of region is very narrow. So we denote this region, okay, omega epsilon, okay? So the width is order epsilon regions. And if the width is different on each path, okay? For example, okay, so dx is in some sense some, okay, yeah, width of each path, okay? So, but this dx is different on each path, okay, that is dj. So, in this case, if we take the limit as epsilon going to 0, then this thin domain problem is reduced to this, okay, one-dimensional problem. And the width of path appears here. So, and if, okay, dx is dj, okay, on each omega j, then, okay, this problem, okay, again reduced to this problem. So the equation is same. So because if we put dx, dj, then this constant is cancelled on each path. So on each path, same equation is supported like this. So, but this dj just appear in Kirchhoff boundary conditions like this. So this dj just correspond to the width of each domains. Yeah, and this condition is same. So this is okay. Some condition correspond to the continuity of function u. So anyway, this problem is reduced to this problems on the Microscopic graph. And actually, okay, also this problem can be reduced to this problem by some transformation. So in that sense, okay, this kind of problem is yeah some universal universal equations. Okay, in sense. So okay, yeah. So now okay, we consider this kind of problem. So some okay weight is imposed on triple boundary conditions. Okay, yeah, now, okay, I first, okay, introduce Yanagi-san's result, okay. So Yanagi sensei just proposed, okay, 5 kind of methodic graphs. Okay, type 1 is very simple. So this is just an interval, okay, and with Neumann boundary condition. And D1, okay, D1 is okay, this DJ, yeah, the width. So that is on this interval, okay, D1 is constant. And another is the okay, circle region with periodic boundary conditions. So this region and this region are very trivial in some sense. And from type 3 to type 5, yeah, I will explain. So the type 3 region is like this. Yeah, one segment and one circle, and with triple boundary condition at this junction point. But D1 and D2 are different in general. Okay, so this means, okay, the width of omega 1 and the width of omega 2 are different each other. Okay, so yeah, please remember, so this D1 and D2 just correspond to the width of each region. And as a limit of this region, okay, this problem, okay, it will reduce to this problem. And this width is just appear here. So anyway, so D1, D2 there. And another type 4 is the connection of 2 circles, like this, still D1, D2. And type 5 is, okay, circle and segment and circles, okay. So Yanagi-san just consider this, okay, these 5 kind of regions. Okay. So this is an example of type 5, okay. So for example, okay, for type 5 region, we consider this kind of problem. So in each graph, okay, we consider this reaction diffusion equations. So in this case, same equations. So, but boundary condition, in the boundary condition at George junction point, okay, becomes like this. For example, at this junction point, okay, D1, okay, some weight D1 and D2 are imposed like this, and it equals D1 like this. Okay, similar here. So, okay, and for these, okay, 5 type of methodic star graph, Yanagi-san just proved this result. Okay, as theorem one, okay, if okay, methodic star graph is one of type 1 to type 5, then any non-constant steady state is unstable. That is, okay, the localized patterns are necessarily unstable if we consider from type 1 to type 5. And if, okay, and this is the second theorem by Yanagi-san. If the methodic star graph G is not none of type from type 1 to type 5, then okay, we can take nonlinearity if you appropriately such that there is this stable non-constant steady state. That is, if we take appropriately nonlinearity, then okay, there exists some localized, stable localized state. So this is a result by Yanagi-san. So so now we just concentrate our interest to 711. That is, the Anderson just emphasizes if the metric star graph is one of type 1 or type 2 or type 3 or type 4 or type 5, then, okay, any non-constant steady state is unstable. So we consider this problem from the viewpoint of pulse motions. So it is the purpose of the first part of my talk. So, okay, now consider, okay, this kind of problem. So, okay, for example, type 1 and type 2 is clear. So this is just interval. So any non-constant service, any non-constant solution is unstable if equation is a scalar equation. Type 2 is also the same. So in that sense, we type 3, type 4, or type 5 are interesting. So first we consider the type 3 case or type 5 case. Okay? And we consider some scalar reaction diffusion equation like this. And please consider Arenkan equations as the typical example. Okay, so then and we suppose this equation has some front solution like this. So we put front solutions as the initial data like this on the interval region, and this part we just suppose it will be close to +1. Now we consider for simplicity we just consider this nonlinearity only. Okay, so the u equal ±1 is stable equilibrium of this nonlinearity. So for simplicity we consider this nonlinearity only here. So then we put this initial data first. And also, quite similarly, also for the type 5 case, we just one front solution on the interval, and on this line, we suppose u is close to -1, and on this circle, u is close to +1. So we consider this. So, and how is the movement of front solution? So this is a result for a type 3 case. So if we put a front solution inside data like this, then how is the movement of this front solution? So L denotes the location of front solution. Then so this is small. So but this is the L dot. So dl dt. So dl dt. So it's essentially governed by this ordinary differential equation. So of course this is very complicated. So but now here d1 this so this is just correspond to the width of each region. So and L1 and L2 is the length of each graph. So that is L1 is the length of this segment, and L2 is the length of this circle. So then the movement of L is governed by this ordinary differential equation. So dl dt is almost equal to this nonlinearity. So and we understand from this nonlinearity, if this part vanish, so it means the ratio of d1 and d2 is 2 and 1. So in that case, this part vanish. So then, if this part vanish, then at the same time this part vanish. So then this part are cancelled, and eventually, if d1 minus 2d2 is equal to 0, then this right hand side becomes like this. So then this means there is some unstable point And if initial data is here, then it moves to here. And if initial data is a little bit left-hand side of this critical point, then it goes to left. Like this, okay, this kind of okay front solution is unstable in something. That is okay, no stable stationary front solution like this. So this means okay, this result is consistent with Yanai-san's result. Actually, okay, Yanai-san just proved if okay in this metric star graph and the ratio of D1, D2, and 2 and 1, then, okay, no stable, non-constant steady state. So, but from the viewpoint of the movement of front solution, it is just explained from the viewpoint of the motion of front solution. And by using this ordinary differential equation, we can know a more precise movement like this. So if so, L1 and L2 the length of this of each graph. So and okay, addition to this condition, if the ratio of length is 1 and 2, then the dynamics becomes like this. So, okay, it means okay, if okay L1 and L2 equal 1 and 2, then okay, no, okay, no critical point, and any front solution okay goes apart from the junction point like this. If not, okay, then there's some X star and this just take a load of separatrix. But if in this ratio, no separatrix and front solution monotonically apart from the origin. So this and yeah, and like this, okay, we can consider the very precise movement of front solution in a type 3 metric graph. And quite similarly, for the type 5 metric graph, we also consider the movement of front solutions like this. So this case is more complicated. So Yanaiga-san just considered this case only. So so I just go up. Yeah. In this case, Yanai-san just consider only this case. The ratio is 1 to 1 case only. So, but by applying the front dynamics approach, we can get this kind of ordinary differential equation. So this is very complicated. So, but at least if the ratio of D1, D3 is like this, then okay, these parts all vanish, and eventually the movement okay is reduced to this equation, and we understand why okay no stable stationary state okay from this ordinary equations. And additionally, okay, we can also another condition by using this ordinary differential equation. Okay, this condition is not necessary. Actually, if D1, D2, and D3 satisfy this condition, similar movement can be observed. And if some ratio, some relation between D1, D2, D3, okay, are satisfied, together with the condition for the L1 or for the LJ. Okay, yeah, LJ. Okay, LJ is the length of each graph. So then, okay, this dynamics change. Yeah, some okay, some several different motion here. Yeah, in particular, if there is another ratio, and L1, okay, L1 is the length of each graph, okay, is in some sense sufficiently large. Then, okay, there appears some stable stationary state like this. And but the length is a little bit smaller. Then, okay, this stationary state become unstable like this. Yeah, okay. As a summary, okay. So now, okay, as the extension of Yanagi-san result, okay, we can consider the movement, okay, from solution of Alenka equation precisely, and yeah, and it gives the another understanding for the movement, another understanding for the stability of front solutions. Including the result of Yanagi-san. Okay, this is the first part. Okay, okay. So now already 3 o'clock. Okay, 2 o'clock person. Yeah. So this is the first part, and second part. Yeah. Okay. So I skip the detail of the second part. Okay. Yeah. For the second topics, I just mentioned about the mainly purpose only. Okay? Yeah. Yeah, in the second topic, okay, yeah, okay, how, okay, macroscopic structure can be observed, okay, by the influence of microscopic structures like this. Yeah, actually, okay, the macroscopic, okay, skin patterns, okay, okay, influence from the microscopic structure of skin cells like this. And skin cells has the some microscopic networks such as signaling network or metabolic network. So, and we would like to make clear the relation between this microscopic structure and macroscopic structures. So yeah, actually, okay, yeah, this is okay. Some precise explanation. So, for example, okay, so let's consider the skin pattern of the zebrafish. Okay, so we can observe the some stripe patterns for the as the skin pattern for zebrafish. So, but in the microscopic level, okay. There are two kinds of skin cells. Okay, like this. Okay, one skin, it looks yellow, and one skin, okay, looks black. Okay, so and they interact like this in microscopic levels. Okay, locally, okay, they inhibit each other. So, this has some long range interactions by projections. So projection means they just using a hand, and they interact some cells a little bit far from itself. Okay? So from very distance far from cells like this. That is okay. In a macroscopic level, okay, local inhibition and long range activation. Yeah, like this. Okay, very complicated. And another example is the so-called proneural waves. Okay, observed in brains of fruit flies. So, okay, proneural waves is one kind of the traveling waves. So, that is okay. In the microscopic level, okay, each cell, okay, interacts, okay, very complicated. So, and eventually, okay, some cell just differentiate another cells in the brain. So, but this differentiation just propagate very regularly like this as traveling wave solution. So this is a conceptual movie like this. So yeah, each cell just change to another cell. So but the propagation of change is very regular, like traveling wave solutions. So in that, in this sense, okay, so this traveling wave-like movement is in macroscopic movement. So but such macroscopic movement is coming from this microscopic structures. Okay, so how can I explain this phenomenon? Okay, so to overcome such problem, we have one strategy by using the integral kernels. For example, normal diffusion is just given in the For example, the normal diffusion is just expressed by this integral kernels. That is so this is a very short example. So if Wnx is the sum quantity at time n step and log x, and then next n plus 1 time step is just given by this convolution of k. That is the n step state just influence to next time step by this integral kernel. And if we use this expression, for example, diffusion case, we expect the kernel is like this. And a projection case, the projection means some cell just influence the another cells with some distance. So in that case, we consider this kind of kernels. Like this. By using kernels, we express diffusion or some projections. So by using this expression, for example, so this is some typical example of the activator inhibitor systems. Yeah, this is a activator inhibitor system. So if U and V are activator inhibitor, then they interact each other like this. They, for example, U activate V and V inhibit U, and self inhibition and self activation like this, and U diffuse with diffusion constant D1, and V diffuse with diffusion constant D2. And if the diffusion constant of activator is sufficiently small, then we usually know some Turing patterns appears. And actually, if we express this relation in a model equation, yeah, maybe this is some typical model equation. That is, U sub t is a D1 Laplacian index. So this is a diffusion with diffusion constant D1, and this part is the U activate self-activate and inhibited by V, and activate V and inhibit self-inhibition like this. So yeah, like this. If we express this state in a model equation, so this is some typical model equation. So and in this case, we usually observe some Turing patterns. So but why this relation? But why this kind of patterns appear by this relation. So no theoretical explanations. So but Gila and Meinhardt just suggested this kind of explanation. Okay, that is, eventually, okay, this relation leads the this condition, that is local activation and long range or long-term inhibition. That is, okay, diffusion constant D1 is sufficiently small compared with D2, and U activate V, and V inhibit U. So as the consequence, this relation causes this kind of effect. So this is essence to produce this kind of Turing pattern. So this is a suggestion by Gill and Meinhardt. So, but if we express this property by using integral kernel, so this just means the integral kernel is Mexican hat type profiles like this. That is local activation just corresponds to this part, and long-term inhibition just like this part. So, and totally, this property just corresponds to the Mexican hat profile integral kernel. So this is okay believed for a long time. So, but there are no, theoretical explanation between okay Mexican hat type integral kernel and activate inhibitor systems. Just a belief only, expectation only. And this is a numerical simulation by using Mexican hat type integral kernels. There are several patterns that can be observed by using this. And also, okay, Kondo-san, okay, in Osaka University, just suggested, okay, in nature, okay, there are so many complicated patterns, and in general, okay, such complicated patterns are very hard to express by using reaction diffusion systems. So, but if we take appropriate integral kernels like this, then okay, we can easily appear such complicated patterns. So this is some example. So if okay, so this is the shape of integral kernels. Then some pattern okay appear like this, and this pattern is very complicated. And usually, okay, we don't know any example of reaction diffusion systems expressing this pattern. So, but we take this kind of integral kernels. Okay, these patterns can be reproduced easily, and this pattern more complicated. So, okay, so this is okay some network structure, in some sense. So, and this is very complicated and very hard to express by reaction diffusion system. But take this kind of integral kernels, this is also very easily So this is two. So okay, like this, okay, okay, macroscopic patterns are determined by integral kernels like this. So we can, if we can take appropriate integral kernels, okay, we can reproduce the various macroscopic pattern easily. So and on the other hand, such integral kernels, okay, should be given by microscopic structures, such as this kind of microscopic network. So this is a problem. And if okay, we succeed this, succeed to solve this problem, then we can get some okay direct path from microscopic level to macroscopic level by way of internal kernels, like this. So then, so we just consider the very, first, the simplest case, active infinite case. So, in microscopic level, this kind of very simple network system exists in microscopic level. And we believe, this microscopic relation just produce this kind of Mexican type internal kernels. But we don't know any theoretical explanation. So, but now, we get some a method to connect between them. So this is a very rough, very rough, explanation for this method. So this is activate inhibitor system with diffusion constant D1 D2. So so then this system is easily expressed by this modification in the linearized sense. So C1 C2 here B1 D2. So we just write this modification in a vector valued form, in this form, and D is the diffusion matrix, and A is the C minus C3. So expressed in this function. So this function just means with inhibitor system. So and then we take Fourier transformation. So then this vector valued equation becomes this kind of equation in the Fourier space. So then if big C is the matrix here, then this equation in Fourier space becomes like this. So and if the eigenvalue of this matrix, so lambda max, yeah, this is two two square cubic square matrix. So there are two eigenvalues like this. So we take beta 1 as lambda max here. So then the beta eigenvalues is dominant for this dynamics. That is, the solution of this equation eventually converge to this function. Correspond to the maximal eigenvalue and associated with and the eigen function associated with this maximal eigenvalue. So so that is asymptotically this solution converge to this. So then this means that each element satisfy this equation. That is this part. In each element, this part appears. So that is the any element of this vectors satisfy this relation. So we call this effective equation. And if we can take inverse Fourier transformation of lambda max C, then this equation becomes this kind of equation with infinite kernels. So but usually lambda max C is not belong to L2 space. So this inverse Fourier transformation cannot be taken. Now already time. So then so we change the several things. So yeah, this is some technique. I skip all of things. So but by a little bit modify this part by using the Lambert function or like this. So and we eventually we reduce this problem into this kind of problem. And this function belongs to the empty space. So we can compute the inverse to Fourier transformation. Then, okay, eventually we get this kind of integral kernels. So, okay, and by using this method, okay, we use and the integral kernels, then we can get Michigan hat type profiles like this. Okay, like this, okay, at least for the activated integral system, we can get theoretically Michigan hat type integral kernel. So we can understand why Turing pattern appears. So, okay, so we would like this method to a more complicated, more general case. So, okay, I just use, okay, 2 minutes, okay, and okay, okay, by using this method, yeah, we show several applications. Okay, as the typical applications, okay, please consider this type of network systems. So this is a little bit complicated. So U does not move, no diffusion. So activate each other self inhibition. So then, what is the effective kernel of this system? So in fact, okay, Macron, okay, in 2016, okay, he just made many computation by using this system, and Macron just emphasized, okay, also this system produced the similar spatial profiles to Turing patterns, but he doesn't know the reason why this system produced Turing patterns. So, but by applying our result, okay, and compute the corresponding integral kernels about this network system, okay, we can, okay, compute, yeah, by applying our procedure. Then, as a consequence, okay, we get Mexican hat type profile. That is, okay, also this system, okay, produces a Mexican hat type integral kernel. So, Turing pattern is naturally, okay, reproduced by this system. And another is, okay, more complicated case, okay, so the scheme patterns. So, and I skip everything. So about we get this kind of integral kernels, and by using this integral kernels, and this is numerical simulation by using this reduced integral kernels. So then we reproduce the similar scheme patterns of the zebrafish. So actually, okay, Nakama-san in 2009, okay, she considered the many experiments and many numerical simulation by using another model equation. So she okay produced this kind of patterns. So, but the similar patterns to them reproduced by using this integral kernels. And yeah, this is the last example of, okay, the polyneural wave, okay, some traveling wave patterns observed in brains of fruit fly, like this. So also in this case, okay, the microscopic structure is very complicated. And yeah, actually, so this is a okay, a similar network system about this. And there are, okay, already there are some model equations. So, but this is very complicated and no theoretical analysis about this. So, and about some linear traveling wave are observed by this model equation. And if we change parameters slightly, so some of the salt and pepper patterns are observed. So, yeah, this is okay, some numerical simulation. If, okay, for example, we change this coefficient as the variation parameter, then okay, A is a little bit larger, then some okay traveling wave solution are observed. But if A is smaller a little bit, then some okay some dot pattern. So we generally call the salt and pepper patterns appears okay in other models. So about this is a okay microscopic network in this case. So we just apply to this network system. Okay, we apply our method to this network system and get internal kernels like this. Then okay, quite similarly. Okay, if A is a little bit large, then okay, some traveling wave reproduced by using the internal kernels. And if A is small, then the reduced internal kernel becomes like this. Then some okay, salt and pepper pattern are also reproduced like this. Okay, so this is concluding remark. And yeah, sorry, I skipped the details. Yeah, I don't have enough time. So okay, this is concluding remarks. So thank you very much.
Thank you so much for this talk. Any question or comments?
Hey, Sensei, may I ask a question?
Yeah, please.
Thank you for your interesting talk. So in the second part, you used the non-local dispersal to study Turing instability, Turing pattern. And but sorry, I didn't catch it very well. As in your example simulation, you consider diffusion plus non-local. Yeah, next page. Sorry. In your simulation, you consider diffusion, random diffusion plus some integral. Yeah, okay. So my question is, so the convolution and this diffusion, so what's the difference if we drop the random diffusion?
Yeah. Yeah. Okay. Okay. So, actually, okay. Diffusion is also okay expressed by okay integral kernels. So, of course, okay. In that sense, okay. You can represent this only by integral kernel only. So, but yeah. We just use it. Yeah. We just use this expression because okay to remain diffusion term itself is very okay useful and appropriate for reproduce some patterns. Okay, so it is of course just experience. So yeah, but yeah, if okay, we approximate this part also by integral kernels, yeah, and then the accuracy of approximation is a little bit worse than okay when we use the diffusion itself. So yeah, it's just experience and no theoretical explanation.
Okay.
So but yeah, as the experience, so to remain diffusion term like this is better.
Okay.
To reproduce some patterns. So
Thank you.
cannot
Yeah,
explain
it's
well.
very amazing. Very.
Yeah.
Thank you.